Okay, so today, electron configuration. Okay, electron configuration. So hopefully by the end, you understand how they come about and how to do them, okay? So there's 3 rules that are used to build electron configurations. These 3 rules, as I describe them, will kind of tell you how to do electron configurations. It's the Aufbau principle, the Pauli Exclusion principle, and Hunds Rule. Okay? So the Aufbau principle is the German word for Aufbau, means to build up. So build up is Aufbau. Okay? Pauli Exclusion principle talks about electrons. We'll talk about how they go in. And the Hunds Rule sort of is how they kind of order themselves. The electrons, how the electrons order themselves. Okay? So we'll talk about these in order. So don't be so crazy about getting all these written down or everything, because I'm going to talk about each one individually, okay? So let's talk about the first one, the Aufbau principle. Okay? Here's the principle. Electrons occupy orbitals of lowest energy first. So that means every one of your electron configurations will start out with the same symbols, 1s2, because that's the lowest energy orbital, 1s2. That's what the Aufbau principle means. Okay? We don't like start at 6p and then go to like 3s and then back up to 4, whatever. We always start and go in order. Okay? So let's look at this picture really quickly. And so you guys don't have to write it down. I actually have a handout for you, okay? So again, if we look at this really closely, you'd say, oh, this makes sense. 1s, 2s, 2p, 3s, 3p, 3d. Oh, wait a second. 4s kind of snuck in there under 3d. So what that tells you is that for whatever reason, the 4s sublevel, or the 4s orbital, is actually lower energy than the 3d. So an s with a 4 is lower than a 3. It's like, well, that's silly. Why do you have a 4 lower than a 3? The reason has to do with how these main energy levels break down. Turns out that if I was to go look at energy level 2, notice there's a 2s and a 2p. See how they're split apart? Well, those both come from the same Niels Bohr's number, energy level 2. And if you were to actually draw his energy level, and what you'd see is the level 2 is actually right there, and what happens is the s orbital is a little bit less energetic, and the p is a little bit higher. So they sort of split. In fact, these are called, this is the main energy level, these are called the sub-levels of the main energy level. So they split. What happens is the splitting occurs as you see some crazy things happen. If you look at level 3, I'm trying to sort of put it between these 3, so the s pretty far in energy, P, and then the D. So this would be maybe a 3 there, okay? Something like that. And what happens is the 4, my goodness, there's a 4, S, P, D, and F. The actual energy level 4 is probably somewhere up there. And what happens is the S sublevel just is lower in energy, and the 3 level of the D goes up in energy, and the D just ends up being a little bit more energetic. What that means for you guys is that when you get to argon, which is 3p6, you go to 4s2, and what you want to normally what you want to go is you go, oh, here's the D block. You're really excited because now you get to use D's for the first time. You're like, yeah, I'll get to use the D's, and then you go 4D and you start counting, but it's actually the 3D level. Okay? Now, take your sheet of paper and look at this periodic table right there. Right now, look at it. Notice how it actually shows that for you. Right here shows you that the 3D, then the 4D, and the 5D, you have to phase shift them down one, basically. So you need to remember that. That's probably the only thing you need to remember. Okay? So those are the energy levels. So that means when you do an electron configuration, you'll actually write 4s, then 3d. Okay? Let's go on to the next rule, the Pauli Exclusion principle. It's really simple. It says an orbital can hold only 2 electrons, and they must have opposite spin. Okay? So, here's the first one. 3 electrons. Can't do. No. Here's another one. Wolfgang Pauli says, no, you can't do it. It's too energetically unfavored. Likewise. Can't happen. Okay? You can have 1 electron in there, that's fine. But when the second one comes in, it has to be opposite spin. Okay? And the rule is only 2 electrons per orbital. Only 2 electrons per orbital. Okay? So really the only things Pauli exclusion principle says, 2 per orbital and opposite spins of the electrons. Okay? See people writing that down? Pretty much finished? No? No? Okay. Okay. I just want to show you one thing here. Notice that here they have 1 line, right? Notice here they have 3 lines. What does each one of these lines represent? An orbital. And so each one of those lines can have how many electrons? 2. So that would be 6. Notice there's 5, right? And the F, is there 7? Yeah. Perfect. 1, 3, 5, 7, 2, 6, 10, 14 electrons. Okay? Hunds Rule. This is the last one. Oh my gosh, there's a lot of writing. So while you guys write, let me explain it. I think it's easier just to show you. I'm going to just take a d orbital, any d orbitals. So I'm going to draw 5 lines. Okay? 5 of them. What Hunds Rule says is the first electron comes in and goes, oh boy, lots of space for me. I can go wherever I want. So the first electron can go like this. Oh, just an aside, people, from now on I'm going to write electrons like this. Okay? Those are my arrows, just so you know. So the first one could come in like this, or it could come in like this. Doesn't matter. Okay? So we'll draw it in like this. Now the second one comes in and goes, oh, da, da, da. Now there's all this empty space, but the second one, I don't know, they're friendly or whatever. They come in and go, oop, like that. Hunds Rule would say, you can't do that. Because you have all this empty space here. You have all this. You have to go there first before you pair up. Okay? So bye. So the second one has to go here. So he comes in and he goes, okay, there I am. I'm happy. Hunds Rule would say, no. Once the first one comes in with the positive spin, you have to come in with the positive spin as well. Okay? That's what Hunds Rule says. You have to be the same spin. Turns out they have to be parallel to each other. That means the third one comes in like this. Fourth one has to come like this. Then the fifth one comes like this. Now once the sixth electron comes in, there's no, they got to pair, right? They got to pair up. But when they pair up, they have to be, remember what Wolfgang Pauli said, they have to be opposite spin. And then they'll go like this. Okay? Just like that. Yes?
5 times.
5 times? 1, 2, 3, 4, 5. D orbital. D orbital. Okay? 5 orbitals, 10 electrons. Does that make sense? 10 electrons. Okay? So the same thing could be for 3, right? 1, 2, 3. A p orbital. They'd have to go like this, then like this, in that order. Or they could come in with a negative spin and they all go in negative, then they all go in positive like that for the p's. Okay? You guys got it? Do you get this analogy? When you're in there, yes, Ferris.
Will their spins matter?
Yes, their spins matter. Turns out if they're in both the same up spin at the same time, that's energetically in favor. They have to be opposite spins. And whether they come in, but that doesn't matter whether the first one's up or the first one's down, absolutely not. There's a 50-50 shot of it either coming with a negative or a positive.
So, do we ever have to write it like you just did?
Yes. So you'll have to show, there'll be pictures and tests where they'll show which one of these is an appropriate Aufbau diagram with the electrons in it, and there'll be ones with spins, opposite directions and stuff like that.
But it doesn't matter if it's negative or positive first, right?
No. So again, this first electron has to come into the first p orbitals. It could come in like this or like that. Either way. Okay? But then that one sets the tone for all the other ones. Does that make sense? Okay. So, let's look at one. Here's the first one. There it happened. Notice the arrow came in. Now, it could have been up or down, but it came in up. This is the Aufbau diagram for hydrogen. Right there. And I would write 1s1. So, what do you think the next one's going to be? Helium. So, where's the electron going to go? Here, here, here. And it's going to be up or down? Down. Okay. You guys are pretty smart. Oh, boy, look at this. This is exciting. Yeah. 1s2. That's it. What do you think the next one is? Okay, let's see. Here it comes. There's lithium. Okay. And then what's the next one? Beryllium. Then where do we go to? Boron. So now we've filled up the 1s, the 2s. Now we're going to the 2p. Oh, by the way, there is a little mistake here. Just want you guys to know. There should be 5 boxes there. Okay, it's just a little bit of a mistake. So let's go to the next one. There's boron. So now where's the carbon? The next one's carbon. Where's that electron going to go? Here? Here. It can go either here or here. It doesn't matter. But we'll put it there. Okay? And should the spin be up or down? Up. Good. So you guys got it. This is really dynamic, isn't it? Not really. There it is. So, what's the electron configuration of carbon? Everybody go with me. 1s2, 2s2, 2p2. That's what you would write down on your sheet of paper. 1s2, 2s2, 2p2. Easy. Right? It's just 1s. That's the level, and there's 2 electrons. 1s2, 2s2, 2p1, 2. It's like an accounting system. Okay, we'll skip nitrogen. That makes sense. And now when we get to fluorine, this is the one that Marshall did on the board. 1s2, 2s2, 2p, 1, 2, 3, 4, 5. Okay? And how do you know this? If you look at that periodic table, it basically is the same thing as this. It's just reading it across like a piece of paper. You just start here, you go 1s, then 2s, then 2p, then 3s, then 3p. You just go across on that periodic table for the blocks. So let's look at this, and so there it is right there. You start out, you just read it like a book until you get to the element you want. Let's say you want to get to vanadium. You go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3. You write 3d3. You write all that down. That would be vanadium. Okay? Yep, all of them. We're going to talk a little bit about that. So this is called, all of them is called standard notation. Okay? The ones are the main energy levels. The orbitals, the sublevels are the orbitals. Orbitals are sublevels. And the little red superscripts, those are the numbers of electrons. Can I ever have the number 3 or 4 here? No. Could I ever have the number 8 here? Could I have the number 4 here? Yes. Okay? Can't go over 6 for P's. Can't go over what for D's? 10. And for F, we can't go over 14. Okay. Now, while you're writing that down, let's say I go to Alondra and I say, hey, Alondra, I want you to give me this one. I want you to give me these those standard notation for cesium. And Alondra's like, I got this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, then you get here and you're like 6s1. That's a lot. There's a cheating way to do it. The way you do is you find the element they give you. They call it shorthand notation. And say cesium. Where's the next row up? Where's the noble gas? You go, you find it. Oh, it's xenon right here. So you just take and write in brackets, XE brackets, and then you write 6s1. That would be the shorthand. Okay? Does that make sense? So, let me pull that up really quickly. Let's do the shorthand for, this would be for cesium. You could do all this 1s2, blah, 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 or you could write XE 6s1. So that would be shorthand for cesium. You have to be able to do both ways, okay? Both ways. Yeah, and so in fact on your homework today, the first 7 are longhand and the bottom 7 are shorthand, okay? So here's the notes for shorthand, so if you want to go ahead and write these down, you can. Use the last noble gas that is located in the periodic table right before the M. Yep, you go always to the end. What? Well, you know what? Just go to the end of the row before. You'll get a noble gas. So if I ask for rubidium, you would go to krypton and then go to rubidium. If I ask for potassium, you could use argon. Sort of before that, we normally don't bother. Like, this is not much of a shorthand. The longhand is 1s2, 2s2, 2p5. The shorthand is helium in brackets. Okay? This is a bad example. I should change that. That's it. Yep, basically that's it. I'll put these back up and then I'll go ahead. So this homework is assignment number 42. So write that down and it's due tomorrow. For the last 10-15 minutes, I will come around as you raise your hand and help you. I would advise that you have this sheet out and you look at this periodic table as you try to do these. The ones that say try are try. I'm not going to help you as much out with those as I am going to help people with just more simpler ones, okay? Yes, there's going to be 2 problems like this on the quiz, much resembling the warm-up that you did today. 42. I actually had students get this done in 10 minutes in class. Did you guys hear me? I had students get this done in class.
Which one is homework, Mr. D? This one or you?
Well, what do you do on that one? Why don't you read that and tell me where's the problem for that? You have to, in fact, what's the title? Reference sheet. Yes. What? Better example is that one? Okay, I will. So let's do an example for calcium, okay?
Oh, I got it.
Calcium, okay? This is how I'm gonna write it. So I went to argon, see, the row before, and then 4s2. Does that make sense?
Yeah.
Okay? Yes. Except for look at there.
Did you get this proxy?
Sorry?
3D.
Because I was kind of explaining, that's the thing where I was explaining one energy level kind of drops and the other goes higher. So it turns out that just for whatever, the 3Ds go up in energy as they go up, and then the 4S's go down from the 3s go up, and then the 3Ds just end up being slightly more energetic than the 4S's.